I don't ever slow up, no I don't take sh**. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take sh**. I got no love for the fakeness. If you want.
And we're rolling. Electrotechnics N6. Okay, so we are looking at the generation and supply of AC power. Generation and supply of AC power, which is this power that you're seeing right now. Right? There's load shedding, but yeah, you know what I mean? Now, when generating power and supplying this power from ESCOM, wherever that power is coming from, right? Coming here to where we are right now, right? We have got some losses. Are we together? Now, we've got something that you call power factor, right? Or PF. Power factor is the ratio. It goes by many definitions. Trust me, many definitions. And there are many ways of calculating power factor as well, right? But I'm going to give you the simplest definition. Power factor is the ratio of true power and apparent power, right? Apparent power. Now, true power is the actual power that we receive, right? And apparent power is the power that we're supposed to get. Does it make sense?
Oh, yeah.
Yeah. So if I send 100, what bank do you use?
Capitec, FNB, Standard Bank.
I will use FNB as an example because I use FNB as well, right? So if I'm to send you 1,000 rand right now into your FNB account, the 1,000 rand is an example of apparent power.
Yeah.
Because theoretically, if I send you 100 rand, you're supposed to theoretically receive 100 bucks. Are we together? But then according to bank charges, how much will you get if I send you 100 rand, 1,000 rand? 950, right?
Yeah.
Because the bank is going to take some money. So 950 is the actual amount that you received. Are we together?
Yes.
So you've got apparent power, which is what you're supposed to get, and true power, which is what you actually get. Are we together?
Yes.
So power factor is the ratio of true power to apparent power. Now power factor is also given as a decimal. Are we together, right?
Yes.
Like 0 point something, 0 point something, 0 point something. That's power factor. Now, we've got what we refer to low power factor. That is when your power factor is 0.3, 0.4, 0.5.
Yes.
That means we've lost a lot. Right? Because if your power factor is like, let's say 0.99, that means you're getting like 99% of everything that you're supposed to get and only losing 1%. And if your power factor is 0.5, you've lost 50%. Yeah, that's not a good deal. So let's look at the effects of low power factor, right? First one is electricity becomes, I'm always interested about the money, right?
Yeah.
Oh yes, money first. It becomes more expensive. Yeah. Low power factor makes it very, very expensive. Number one, for the one who's buying the electricity, because you're buying like 1,000 rand and only getting 50 rand. Yeah, that's a loss. So it becomes more expensive. That's number one. And number two, because in order for us to compensate, right, for these losses, we're going to need thicker cables. Are we together? Yes. And thicker cables are heavier, so they're going to require more pylons to hold it up. Are we together? Right? Now, let's move over to another one. Because you need to compensate for that, right? That is going to raise the level of current. Yes. Are we together? So, low power factor raises higher current. Are we together? Now, here's the thing with electricity now. The higher the current, the higher the losses. Are we together? Yeah. The lower the current, the lower the losses. Are we together? So with high current, you end up with high losses. Are we together? Yeah. High current, you end up with very, very high losses. So that's another disadvantage of low power factor. And another thing as well is, yeah, this is absolutely very true. It is less efficient. Low power factor is less efficient. It is not really efficient when you're using low power factor. Now, I mean in terms of the equipment that you're going to use, right? Yes. So let's have an example using an electric motor. That electric motor is not going to function at 100. Yeah, my English is off. Now, that electric motor is not going to function at 100%. Because of low power factor, because most of it we're just not using it. Are we together? It's not even getting there. Now let's look at the methods of raising the power factor, because it's very, very beneficial for us to have a very high power factor. Are we together? Yes. So method number one is you can use you can use, okay, that's what I'm going to make it the last one. You can use inductive motors, right? Or induction motors. You can use induction motors. Using induction motors, right? Now with a low power factor, remember we've got current, we've got an inductor which makes the current lag. Are we together? Yeah, an inductor makes the current lag. So by using induction motors, you can reduce the lagging, therefore fixing the power factor. Are we together? Or correcting the power factor. Then the second one, which is going to be our last one, using a capacitor bank, right? Using capacitor banks or capacitor circuits. Using capacitor banks, with capacitors now, it makes the current lead the voltage. Are we together? Yeah. So in that case, that also helps raise the power factor. Are we together? Right? Let's move over to some calculations now, right? Now, the formula for calculating okay, let's go step by step, right? The formula for calculating XC, right, which is the capacitive reactance, is 1 over 2 pi FC. Are we together? Now, the question that you're going to get from this topic, they would ask you to calculate the capacitance of the capacitors. Are we together? So they'll tell you that the power factor was this low, then we used a capacitor bank, and now calculate the capacitance of each capacitor. Are we together? So we're just going down to the formulas so that we can answer the questions. Or where the actual formulas are coming from. That's where we're starting, right? Where the formulas are coming from. Now, if you want to calculate current in a capacitor, or the current that is flowing through in a capacitor, is voltage divided by XC. Are we together? Okay. So, using this, you can make some mathematics, and then you can say the current that flows through is equals to V over, since X is equals to 2 pi, is equals to 2 pi FC. You can now say I is equals to V multiplied by, because there's 1 over, multiplied by 2 pi FC. Are we together, right? Which is mathematically correct. Right. And then let me write it down. V, because this is that, is equals to 2 pi FC. Are we together? So if a question comes asking you to calculate, I'm anti-formulas, by the way. I don't like formulas. That's why I want you to know where everything is coming from. Are we together? I'm anti-formulas. Then let's look at the next one. Now, power rating, right? Power rating, or kVA rating. Power rating is kVA. Now, the formula for calculating power is VI. Are we together? Yes. That's your formula for calculating your power. Now you can see where this is going now, right? Now, because this is your formula for calculating your power, if they ask you to calculate the kVA rating, right? kVA is apparent power, by the way, right? That's how you know it's apparent power. Because there are no losses. kV is just voltage multiplied by the current, right? This does not take into account the losses, right? The formula that takes into account the losses for true power is VI cos theta, or VI multiplied by the power factor, which is the formula for that. So you can look at your mathematics, and then you can say the kVA, or the power, or if someone asks you to calculate power, what does K mean? 1,000, right? Yeah. Yes. So you can say, you can remove the K, and then you can say is the voltage multiplied by the voltage, right? Which makes it voltage squared, right? Multiplied by 2 pi FC. Because we remove the K, we're going to divide by 1,000. Are we together? This is where the formula comes from. This is where the formula comes from. But your questions, they would want you to determine the capacitance. Are we together, right? They would want you to determine the capacitance. So we have to make C the subject of the formula. Are we together? So it will be C is equals to, I was about to say kVA. VA multiplied by 1,000 divided by, so let me just use the term power, not kVA. Let me just put the term power, because power makes much more sense, right? It's equals to power multiplied by V squared 2 pi F. This is the formula that you end up having. Makes sense, right? Yes, sir. Sweet. Now, let's move over to three-phase, right? So this is only for single phase. I'm sure you've noticed the difference between single phase and three-phase is that here we're only using single phase. Now, if we're moving over to three-phase, this remains exactly the same. The only difference will come when we start calculating power. Are we together? Because when you're calculating power in 3-phase, it becomes root of 3 VI. Are we together?
Yes.
That's the only difference. So from here onwards, you can now add the root of 3, root of 3, root of 3, and your calculations will still be 100% correct. Now, let's do this. Let's move over to another formula that I want. It's not really a formula, but it's something that makes sense, right?
Yes.
It's something that makes sense. But this is where your questions are going to come from. Are we together, right?
Yes.
So they will ask you a question, or they will give you a question. Then they will say, let me read the question here. That a consumer takes in a bulk electricity of 5 megavolt amperes at a power factor of 0.82 lagging. To reduce the megavolt demand, capacitors are installed, which improve the power factor by 0.95 lagging, right? Now, obtain the ratings of these capacitors, right? So now what you're going to do is, the consumer is the one that needs 5 megavolt amperes. Are we together? So that means the load of this thing is 5 megavolt amperes. But then, right, you use the capacitor bank to help fix it. Are we together? Or to help fix the losses. So this is the formula that I'm going to give you. And then from there on, I'm going to explain what each of the following is, right? It says kVA, which is the power, and then this one is for the resultant, is equals to kVA. Then this one is for the load, plus the kVA. This one is for the capacitors. Are we together?
Yes, sir.
Now let me explain the formula. Let me explain the formula and what this formula means, right? So this would be the load, and then this would be the capacitor bank. Are we together? Then together, that will then tell us how much power we're getting. So in this case, a consumer, now let's do this example that I just said. Let me try to give you information on the board, right? Now in this case, it's saying a consumer takes in a bulk electricity of 5 megavolt amperes. That means that if you are taking in something, right, that means that's now your load. Are we together? So the load in this case is 5 megavolt amperes, right? MVA. It's a power factor of 0.82. Now power factor, this is also the losses that we're getting. Are we together, right? But then this lagging, let me write lagging. But then this is too expensive, right? This will become very, very expensive. So in order to fix this, right, you install a bank of capacitors. Are we together? You install a bank of capacitors. Now these capacitors, they reduced the losses. Or in other words, they increased the power factor. Are we together, right? Now, that becomes the resultant. Now, the resultant is what you're going to get. So, for now, we don't know the resultant power so far, right? But we're given the resultant power factor, which was itemized to 0.5 lagging. Are we together, right? And then now the question says, obtain the ratings of these capacitors. Are we together? We're going to use complex numbers, right?
Yes,
So now I'm going to need you to pull out your calculator, and now let us calculate the resultant power first. Or let's start by calculating the load first, because we're going to do all these calculations in complex numbers, right? So let's start with the load. The load is 5 megavolt amperes, right?
Yes,
Yeah, that's not the true power, right? Or that's not the actual power that you're getting. So we need to calculate the true power. And we need to remove mega as well, right? And let's use it in kilovolts, right? Makes sense?
Yes.
Yeah. So I need you to say 5. In order for us to remove that mega, we're going to multiply by 1,000 so that you can put it to kilo, right? So it will be 5,000. Hey, my marker is finishing. So it will be 5,000, right? Multiplied by 0.82. What do you get your answer as? 4,100. Right. So now we have 4,100. Right. And I need you to calculate this for me. Can you say cos 0.82? What do you get your answer as? Oh, sorry, I forgot. Sorry. Say arc cos 0.82.
34.91.
34.91. 34.91. So this is equal to 5,000, right? at an angle of 34.91. Sweet. Now, this is the load power that we have. Are we together, right?
Yes, sir.
Now, let us calculate the resultant power now. Because you know that the resultant power has got a power factor of 0.95, but it is a step above this 4,100. Are we together, right?
Yes,
Or it is above this 4,100. Let's do resultant, right? Is equals to. Now, can you say 4,100 divided by 0.95? What do you get your answer as?
4,300.
No, 4,000 you got? Yes, that one is correct.
4,315.
And 15, comma?
789.
789. Now, you see what happened, right? Is this was the original power, or this was the original power that was taken in by the load, which is 4,100. Now, if you use 5,000, 5,000 is apparent power, right? That's not the correct power that is being taken. So if you want to calculate the correct power that is being taken by the load, is 5,000 multiplied by the power factor, right? That will then give you the correct power that was being taken. Are we together? So if we now have to fix this, right? If we are fixing this by the capacitor, now it has been added by, or it has been improved by 0.95. Are we together? So you're going to divide this power by 0.95, and that will get you this. Are we together? So is this at an angle of, can you say second function cos multiplied by second function cos 0.95? What do you get your answer as?
18,19.
18,19. So the resultant power is 4,315.789 at an angle of 18.19. Are we together?
Yes.
Now, you see the formula that we had, right, is resultant is equals to kVA, is the resultant power is equals to the load power plus the capacitor bank power, right? So the question can say, obtain the rating of these capacitors. We need to find the capacitor rating. Are we together, right? Or in other words, we need to find how much power are these capacitors rated. Are we together?
Yes.
Sweet. So we only need to find the power of these capacitors. Now, this is in polar form. So we need to convert this to a rectangular form. So let's restart again. Now, can you say 5,000 cos 34,91? 4,100.
100,26.
Serious? There's a comma.
Yes.
Okay. So you got 4,000,
4,100,
comma
26.
26. Perfect. And can you also say, now this is lagging. So because it's lagging, it's not going to be plus, it's going to be minus. Are we together? So it will be minus j. Can you say 5,000 sine 34,91?
286,144.
144. That is correct, right? So this is our load in rectangular form. And let's also do the same thing, because you cannot add or subtract in rectangular form. Are we together? Now let's do the same thing here as well. Can you say 4,315,789 multiplied by cos 18,9?
4,100,11.
11.
Yes, sir.
Okay, and it's still lagging, right? So that means also going to be minus j. Are we together, right? So what I need you to do is I need you to also put 4,315.789 sine 18,19. This answer according to the textbook is not correct.
It's not correct.
Yeah, according to the textbook. Let me just double calculate it before we move on. Yeah, it's not correct. It's 2,861,445.
Oh, 445.
Yeah. So the comma is, where is it? The comma, instead of the comma being here, the comma is here. Yeah. Can you give me the answer for this one as well?
1,347, 256.
256. That is perfect, right? That is correct. So that is That is our resultant power in rectangular form. So we've got our power or our load in rectangular form and our resultant power in rectangular form. So now we're looking for the capacitor load. Are we together? Or we're looking for the ratings of the capacitor. Now if you do a quick math, right? kVA of the capacitors is equals to kVA of the resultant. Take this one to the other side, it becomes minus, right? So it's going to be kVA of capacitors is equals to kVA of the resultant minus kVA of the load, right? So that's going to be our kVA resultant. We got it as kVA resultant. We got it as where is it? Yes, it's the last one, right? We got it as 4100.26 minus J 2861.44 minus, and the kVA of the load, right? And the kVA of the load was, kVA of the load is this one, sorry. 1347.256 minus, and then the kVA of the load, right?
Yes.
Which is this one here, right? This is of the load in this one. I should make my work very neat so that I don't cry next time. This is 1, and then that's 26 so that I don't cry next time. Minus J 2861.44. And then you get your answer as. Can you say 4100, comma 11? 4100, 26, and then give you the answer with my head.
4,000.
0,15, that's the answer. Yeah, I'm that confident. Negative 0,15. That's what I got. Confident. Okay, let's move over to the next one. Now we're subtracting, right? So it's going to be negative 1347.256. Can you type it in for me? Negative 1347.256.
It's 1,000 or 1,300.
Yeah. And 47, comma 256.
256.
Now we are subtracting, like minus and minus is going to give us a plus. So we'll say plus 2,861.
Plus 12.
2,861. What do you get your answers? I'm guessing it will be a plus.
It's 1,500. Oh, it's 1,514,184.
That is the correct answer. Are we together? But don't leave your answer like this. Then after this, you now need to convert your answer to polar form. Are we together? Which is this form where you've got this and an angle, that and an angle. Are we together, right? Now, the textbook rounded off this part to 0. Are we together, right?
Yes.
Do I want you to do that? Don't I want you to do that? I don't know. Let's rather not do it now. Let's just do what we have here on the board. So can you say square root of 0,15 squared and then plus 1514 or 1,514 514 14 14. This was 1,515,154. Now I was completely messing with you the last time because whenever you're using capacitors, right? Whenever you're using capacitors, the power factor or the phase angle for the capacitor is always 90 degrees, right? And then the phase angle for the inductors is always 90 degrees as well. So this is your rating. Are we together, right? And if you want an angle, it's always 90 degrees. That's why here the answer is as close to 0 as possible. Are we together?
Yes.
Sweet. So this is the answer. Now